All right, hang
So
on.
you want to start
Just-
recording?
Just a second. It's starting it now.
Okay.
It says it's being live streamed.
Okay,
All right,
done.
I got it.
Got
Okay,
it.
so let's start the March 14th, 2020 Los Angeles Astronomical Society General Meeting.
Second, it's starting it now.
Welcome, everyone. Do we have any new members tonight?
I'm
that
not
would like
new,
to-
but
like
this
to
is my
announce
first time.
themselves?
I'm not new, but this is my first time doing one of the meetings.
Okay, that's pretty new.
Welcome, Tim.
Welcome to you.
I have some serious telescope envy now.
Yeah, well, sign up for the 100-inch night and you can
Yeah,
be in on it.
Well, remember the 100-inch is not a typical amateur instrument. Okay, keep that in mind.
Let's see, the update, I have an honorary live membership for everyone to vote on for Norm Vargas. A little bit about Norm. I've known him for, I think, as long as I've been in the club. I think he was already here when I joined, and that was 18 years ago, I think. And I've seen him at almost any event, every event, with doing stuff for kids at Garvey, just helping out everywhere. Anything else that, Tim, what else can I say about Norm?
Tim?
Well, that's that pretty much does. I mean, Norm's been around. I can't remember when he joined. If he may have even been a member already when I got in '87. Been around a long time. Really enthusiastic. He was our machine shop guy for a long time. And he worked, I think, building car engines someplace. And now, of course, he works running the optical interferometer at Mount Wilson, the Chara array.
Except for Chara.
Yeah, we still see him regularly at Monterey Park when he can come down off the mountain.
He's very, very involved, has been for a long time. And,
Yeah.
I think he deserves this. So
worthy of it.
we talked about it at the last board meeting and we wanted to nominate him and we did, but we have to do that officially at the general meeting and everyone has to vote. So everyone, all eyes, put your hands up or hit your little buzzer things on the store. Okay, everyone's good. Looks like almost unanimous. Anyone not want? No? Okay. All right, so that's good. We'll tell him soon. Want to remind everybody about our dark sky petition. If you haven't seen it, heard about it, or done it, probably the best thing is to go to LAAS.org. Go to our website. It's on the landing page. It's right there, and you can check out the rest of the website as well. There's a lot of information there about all of our locations, what they do, what we do at them. See, other than that, I don't really have anything. We should probably go. Do we need to do a report from the secretary for the group?
I guess our membership is around 850 right now, and doing quite well.
Okay, we haven't had any problems. I think things are coming back. More people are going to be signing up because we have lost a lot of the COVID restrictions and we're going to have a lot more interaction and with outreach and meeting more people. So I expect the membership to continue to be strong and maybe stronger than ever doing that. John, you want to tell everyone how we are financially?
Oh, I was expecting a Lockwood report.
Okay, you can do that. I mean, you got both of them, so have the floor do both.
Okay, can I share my screen?
Sure.
Sure. Let me stop my share.
I'm not seeing the share.
Okay, there. Okay, I've stopped my share.
So can you see my screen?
Not yet.
Not yet.
No? Oh,
I see you.
I didn't hit share screen. How's that?
I see that expensive finder scope.
So
Hey.
that's the club owned Takahashi TAO 130. we've been trying for like the last 5 years to find a home for it out at Lockwood. And we had money set aside for it back in 2019, and then COVID hit. And so we're going to try to get a roll-off roof observatory built for that. And one of our members has generously offered us a 10 by 10 roll-off building. Can you see that?
Yes, sir.
Okay. And so
Where's this?
Really frustrated, baby.
I'm sorry. So the plan is this will have to be, this is a tough shed that's been converted into a roll-off with a split roof down the center. And so the two roof halves roll off to either side. So we have to take this apart in large pieces and haul it out to Lockwood and reassemble it.
I don't
Probably
think
gonna
we're
take
seeing it,
about
John.
4 or 5 people.
I still see the telescope, John.
Yeah, we're not seeing it.
Okay.
It's not the shed behind it?
No,
No.
No.
No, that's the 31 inch.
Okay, my mistake. I saw the Takahashi on an astrophysics mount.
There we
Oh,
go.
there you go.
There we go.
Oh,
So this is a 10 by 10 tough shed that's been modified to be a roll-off roof observatory. It has a split roof, so the two halves roll off to either side. It's on a steel base. And so this should come apart into the 2 roof sections and the 4 walls and the floor. And I think it'll take about 4 or 5 of us a weekend to take it apart and haul it out to Lockwood. So I'm going to be asking for volunteers to do that. I'm going to try to get a Lockwood committee meeting scheduled this month on Zoom. And that'll be one of our major objectives. And then just quickly, the other things that we would like to get done this year. Of course, reinstalling that shed. We want to pour a couple pads in a new design, a 8 by 10 rectangular design to test those out. We want to install 3 pier bases that are our standard pier base design that the committee agreed on 4 years ago, when we're finally getting around to install 3 of them to let people try them out and see how they like them. There's a couple different concrete patch materials on the market now that we want to try out on some of the pads that are deteriorating. So we're going to try patching a couple of those and test that, see how it holds up as a possible repair to extend the life on some of the pads that are pretty deteriorated. On the Explore Scientific trailer, we need to get it connected to the wiring grid, and we want to put a few bunk beds and computer tables in there so people can start using that. On the old trailer, we're going to replumb the sewer line to the old trailer and install a new toilet in that. So hopefully we'll have a working toilet inside the trailer again. And since we've got money set aside to buy the shed for the Takahashi that hopefully we're not going to spend, then I'm going to ask the board to use the savings on that to buy a Wi-Fi controller and maybe a camera for the Takahashi, so that when members want to use it, they just bring their laptop out and just connect it to the Takahashi through Wi-Fi and do their imaging. And so hopefully you'll be able to sit in a nice warm trailer and do your imaging over Wi-Fi and through the Takahashi. We'll have to work out the details about how we reserve time on it, but that's administration. I'm in charge of construction. So that's what we want to get done this year. Been tired of sitting out COVID. We got a lot to get done this year. So hopefully we'll have a lot of volunteers.
All right.
great.
That's my Lockwood report.
Okay. You want to do financial as well?
Yeah, if I can find it. Now, just quickly, we have $51,959 in cash right now.
Okay. We're doing pretty well. We have some money in the bank. We have money allocated for good projects. And more to come. I'll tell you, I'll pick up for Garvey Ranch. Garvey Ranch is also in the middle of an upgrade. We bought a new mount for the 8-inch refractor there, so that we can do some even better imaging than we have been. Vance and Dave, who is here tonight, have been doing some astounding imaging with the old stuff, but it could be a whole lot better. I was looking at the error correction on the screen that they were looking at, and it's really amazing that they can make up for what the current mount isn't doing. So we have the new mount. It's been purchased. It's there. We ordered some rings to hold the telescope onto it, which are on their way. And a couple of the guys have been going over all of the measurements to make sure that the new mount will marry with the plate on top of the old pier. So we have a machinist ready to do that. I think he's already been there and looked and measured. So whatever we need to do, we can do that in-house. So everything that's moving forward very well. We also loaned out our grinding machine. And I see, Andrea, you're here. Can you tell me how that's going? Are you working on that mirror? Andrea? No, not there. Okay. I thought that they were working on the mirror together with somebody else. Okay. Garvey Ranch is back open every Wednesday night with the restrictions off. I expect people to show up. This is a good place for new members to go. Bring your telescopes if you don't know how to use them. If you do know how to use them, bring them. Set them up on the lawn. This is where we also entertain the public in Monterey Park. We're trying to get even a better relationship with Monterey Park, so the more people that can show up and set up telescopes, the better it will be. We need to get another upgrade along with the mount is a high-speed internet connection there. So the city is integral in that. We're working on them now. We're trying to get a meeting set up. It's difficult with the current schedule, so we're going to have to probably meet not on a normal Garvey night, which is a Wednesday, because the person we need to talk to also has meetings on Wednesday night. So we'll just set one up separately and talk him into giving us a high-speed internet connection so we can do some online live broadcasting of what Vance and Dave are doing there, and put what we're seeing and that astrophotography live online. And I think this also would be a good selling point for the city. It's part of our sell to get that is they can take advantage of it too and say that we're imaging galaxies from the middle of Monterey Park. So it's good for everyone. That's about it for that. I think Mount Wilson. Tim, you want to do Mount Wilson? We both know about the same amount, I think.
Well, the regular season for programs in Mount Wilson opens up April 1st. So I think we have tours already. Is April 2nd, I think. That's the first weekend. We have tours right away. We're scrambling to get docents. We might be able to do only one tour a day instead of two on Saturdays and Sundays. We'll see how it comes out. And you've already got our 60-inch and 100-inch nights scheduled right for the whole year. So we're already set up for that. And so if you want to look through the 100-inch or you want to look through the 60-inch, get in touch with Daryl and remember to pay for it. That kind of helps.
He's going to get the link sometime.
Yeah. So we'll have our busy schedule of lectures and concerts, and with luck, I'll be leading a few tours.
Okay, I just dropped into the chat all of the dates for the 60-inch and the 100-inch. They're all half nights. They're all Saturdays. The 100-inch is in September. The The July date I see is not there. That's because it's reserved for the photography contest winners for their night. And also how to contact me to set that up if you want spots.
Hey, Daryl,
I don't
nothing's in the
see-
chat. It's not in the
Yeah.
chat.
Nothing's in the chat?
Didn't get there.
Wow, okay, to everyone.
You do, yeah, you might not have done it to everyone.
Did that
Hit
work?
enter.
I did. Nope, it's not in there twice.
I don't
It's
I
still-
don't.
I don't see it. I don't see it.
All right, I'll try it again later when you're talking, Tim.
Okay.
I'll have a chance to see what I'm doing wrong here.
Yeah.
What's that?
No, that's all right.
Okay. Joe, I see you're here. Do you know about Ford? I think we're still closed there, yes?
Well, Ford is accessible now. I haven't been down the road. I would guess that the snow has melted off now.
Oh, good.
So they still have the ski lights on though.
Oh, they do?
Joe,
Yeah, the Holiday
Joe,
Hill
I
and stuff
was
still
up
got the
there.
lights on. Go ahead, Curtis.
Joe, I was up there over the weekend. The gate is still closed.
But we have a key for that.
I'm assuming there's still snow on the road. Yeah, we have a key. Well, we can get it. We can access the gate, and the ski area will be closing on the latest date for the ski area would be Easter Sunday. So that will be the latest date for the ski area. And then we're also planning an event over the Memorial Day weekend at Ford because right now, right, Joe?
Yep.
Okay, great.
Okay, that's it for Ford.
All right. Thanks, Curtis. I didn't see your name. I'm sorry, I didn't see you there.
I'm
Otherwise-
popping in and out here.
All right. Okay. Okay, did I forget anybody? Greg, do you need to say anything about scouts to the group?
Yeah, I will make it an adjunct to your report at Garvey.
Okay.
I've been in communication with the scouting program, and while they can't guarantee anything, the plans are that the camps will be open this summer. The council will be up and running their merit badge programs around the council. So we're going to go ahead and propose our usual in-person classes, assuming nothing changes with the city regulations and so forth. So I will publish that out to the group through our normal communications channel with our flyer. There will be a Wednesday night in June, a Wednesday night in July, and a Wednesday night in August that we'll be using the classroom at Garvey, and we should have the dome open for observing. And in past years, members have participated. It's a regular Wednesday night, so you can just come. You can help with the scouts, or you can bring your telescope and set it up. There's a portion of the class where we send the scouts out to look at telescopes, and they're supposed to write a little log of what they saw and what kind of telescopes they looked through. So I'll get that out to everyone. You can just show up. If you want to communicate with me, I'm available through the board, or my address will be on the flyer for the class. We'll probably get around 60 scouts. They fill up really quick. It's a very popular program, but it's a lot of fun to see the scouts running around, and we can always use a little bit of help. So thanks a lot. And that's a really great site at Garvey. It's right it's easily accessible. We've got a really cool observatory, and we have all the members and a classroom and everything. So it's a great program and a great thing.
Greg,
So
when you
thanks a
send
lot.
something out, when you say to everyone, does it go out to the club? Do you send it to Andy to send out to everyone?
Yes. Yeah. Well,
Okay.
first I go through the board,
Right. Okay.
and once the board has seen it, then I distribute it through the Los Angeles Area Scouting Council, and then also through Andy to membership, so they'll know when they're happening and they can sort of see that. There's also links in there to merit badge requirements and stuff. And a couple of members have helped me. We have a career panel right at the very end, which is going to be around 9:30 in the evening or so. And so any members that had a astronomy or science related career that would be willing to sit on that panel, please come. It's not super formal. You don't have to give a presentation. It's just really great for the scouts to meet people that worked in the various aspects of the hobby that we're interested in. And so let me know if you want to do that. Just tell the scouts a little bit about what you did, and so sometimes they come up with some questions that are kind of interesting. And anyway, that's enough about that. I'll get that through the board at the next meeting, and then we'll publish out the dates.
Okay.
3 Wednesday nights at Garvey all summer long.
Okay. Garvey's is probably the best place to meet the other members. Lockwood is great if you're going to go do observing and do a whole separate thing, but in town close by every week is a place that you can go, and if you know a lot about telescopes, you can come and teach other people that are bringing their scopes that are new people. This is the place to mingle and mix. So I really want to make sure everyone.
If you need help with your new telescope, we can also help you with that.
Absolutely.
Or even if you're a more advanced hobbyist, I mean, one of the things that I like about Garvey is you can get a cup of coffee and ask people that know way more about stuff than you do and get really, really good answers.
Our members really love their telescopes, and they are very happy to tell you all about them. So all you need to do is walk up to one and say, "Tell me about this," and sit down for a while. Everyone has a good time explaining what they do and what they have and helping other people. So Garvey is a great place. I don't think we have anything else.
Yeah, you want to say anything about the school outreach?
Yeah, we are starting outreach again. We're getting.
Good.
I think we have one already. A request. Tim, did you send something to me about that?
Yeah, I sent Steve sent an answer to me, and I sent it to the board a few hours ago.
Okay.
Farragut Elementary School in Culver City. It's their 5th grade science night, and they'll want everybody to be vaccinated or negative test, but masks outside are optional, and they'll be setting up telescopes outside at the school. Exactly where I'm not sure yet, but we will be doing it.
Is that one going on our Night Sky Network sign up yet, or are we just getting restarted?
I have no idea.
I saw there was a date and some people saying they were going to go. Maybe we should check with.
I don't think. Well, Andy would. Well, I guess Evan would post it on the Night Sky Network.
Right.
You may have.
Andy or Andy would post it there.
Yeah.
I was going to ask about Evan. He usually in the past posted to the LAAS group. I haven't seen anything, any messages concerning school program stuff.
Yeah, this first one just came through, and there was some email with the board on, following the guidelines.
Liability issues and the like.
Right.
In any case, I think we have most of that ironed out. People are comfortable with us coming, and we are comfortable going. And that's just probably the first of many, many we're going to get this year after the lull of not having any school nights. So I expect a lot. New members that are interested in doing this, doing some outreach. I'll probably come to Garvey and talk to me or Tim. We're there pretty much every Wednesday, other than these Wednesdays that we're on board meeting nights. And if you're interested, we could talk about that, and we could give you Evan's contact information. He's the outreach coordinator. So it's going to be a lot. So if you can do that, we really need the help. That'd be great. I think we covered everything. Did I miss anything? We should let Tim do some speaking. Let me introduce our speaker tonight. My friend Tim Thompson. I could read off of the stuff here. I mean, you guys can read all of this, but let's say he's pretty accomplished. When I want something explained to me that I don't understand about cosmology or physics or things like that, it's Tim that I go to, because he generally knows the answer, but more than that, he knows how to explain it to me because he knows pretty much what I understand so far, I think. So one of his great talents, I think, is being able to speak to people right where they need to be spoken to understand whatever he's talking about. One thing I don't see here is I hear he's also quite a good chess player.
Well, I did tie for first place in the last tournament at the San Gabriel Valley Chess Club, if that means anything.
And how long was that this year?
That was just finished last week.
Well, outstanding. Congratulations. And Tim is going to speak about one star tonight, Betelgeuse. Okay, Tim, take it away.
Okay, cool.
And everyone mute, put your questions in the chat, and we'll pick them up at the end and just go right through them.
And
Thank
the
you.
link
Thank
for
you,
the
everybody.
drawing it's posted in the chat too.
So you should all be able to see my screen.
That's good.
And
There it is, yeah.
what you're seeing is not Betelgeuse. You know, I thought before I talked about Betelgeuse, I would just give a quick, one slide moment about the James Webb Space Telescope, since it's something everyone is interested in and just what the current status is now. As you may already know, when you launch a telescope, it shakes, rattles, rolls, and breaks things if they're not, adequately secured. So the hexagonal segments for the primary mirror have to be locked down and stowed when you launch. And after all the deployment and everything else gets out and it gets to the Lagrange point, then you have to get those mirror segments out of their locked position in a line. So they released the segments, they moved them around, and when they got to the Lagrange point, they imaged a star and found 18 images because there's 18 segments all scattered around. So they figured out which image goes with which segment, moved the segments around until they got a nice hexagonal pattern of star images. Then they moved them around so that the star images were nice and clean. Then they moved them around so that the star images all came together. And now what they're doing is called coarse and fine phasing, where they move the segments up and down to get within, a fraction of a micron of each other. So they actually present a continuous smooth surface as if they were a single mirror. And that's what they're working on now, adjusting the mirror segments. In a few weeks, they will start calibrating the instruments, and I'm guessing 10 weeks from now, something like that, they will be able to actually start doing science observations and using it the way you would expect them to use a telescope. You can also see from the numbers here on the screen that the sun shield that's doing its job, the fine steering mirror, is down to 35 kelvins, and most of the instruments are way down. The MIRI, the mid-infrared imager, is only 98 kelvins. That's too warm to use at that wavelength. I know it might seem kind of strange for 98 kelvins, 283 degrees below zero, to be hot, but it is. It's too hot to do observing at the wavelengths MIRI wants to observe. But the temperature's going down. Then you can see the temperature on the sun side of the sunshade. So you can see how effective the sunshade is. So sunshade's working, mirror is being aligned, everything's going the way it should. So in 10 weeks or so, being like real stuff come out of the James Webb Space Telescope. So twiddle your thumbs for 10 weeks or something. So now I'll go on and talk about Betelgeuse. So you know where it is, of course, in the upper corner of Orion, which appears to get its name from old Akkadian word meaning light of heaven. Betelgeuse, as Breyer designation, is Alpha Orionis, which means it was the brightest star in Orion when Breyer did his classifications. Now, of course, Rigel is considerably brighter and consistently brighter than Betelgeuse. but you never know. Betelgeuse is a highly variable star, and we'll talk about that in a little while. So it gets brighter, it gets dimmer. Its name, I've just put one paragraph here, just explaining where Betelgeuse got its name, because there's language barriers, mistranslations. Yad al-Jawza, which I'm sure is not the correct Arabic pronunciation. I don't speak Arabic, so I'm probably butchering the language. Refers to Orion being some great central god or central one in old Arabic mythology. It was mistranslated by some European monk back in the Middle Ages, and he put a B where there's a Y. And so it came out Bed or Bad al-Jawza, which turns into Betelgeuse or Betelgeuse or Battlegoose or Betelgeuse, or however you want to pronounce it, because no two people do it the same. So it's a class M red supergiant. It probably is a red supergiant. It may actually, there's a small possibility that it isn't, but I think it's red supergiant is a good guess. And it's a runaway star moving very fast, probably was born in a region projected on the sky, if you can see my cursor, that is somewhere in here between Bellatrix, which is here, and Mintaka on the end of the belt, somewhere in this region, which is called OB1A association. O and B class stars, super bright or concentrated in that region. And that's probably where Betelgeuse is born. It's moving out of there now. So here's where it sits on the Hertzsprung-Russell diagram, way up in the upper right corner where the red supergiants are. 20 solar masses is a high-end number. It might have had 20 solar masses when it was initially, but now it's probably down to, who knows, anywhere from 15 to 19 solar masses. Different sources disagree, and I'll show you that in a few minutes. I say about 550 light years away and 100,000 times brighter than the sun. You'll find, and I will talk at some length in a little while, that the distance to Betelgeuse is maniacally hard to get, extremely uncertain. Nobody really knows how far away it is to a great extent. And all of the other numbers, its mass, its size, everything you want to know about it, its luminosity, all those depend on getting the distance right. And if your distance is uncertain, then so are all those numbers. So in other words, nobody really knows how big it is, how hot it is. It's crazy, and you'll see why in a little while. So to explain how big really is, some of you have seen this chart before. The first panel in the upper left shows the inner small planets of our solar system: Mercury, Mars, Venus, and Earth, in order of size, not in order from the sun. So Mars gets all the press, but it's about half the size of the Earth and a tenth of the mass. Venus is nearly the size of the Earth. And in the following panels, the first object in the panel is the last object from the preceding panel. So in panel 2, the first object is the Earth, shown with Neptune, Uranus, Saturn, Jupiter, going up in size. And so this is so, because you know how big the Earth is, and you have an idea how big the planet is, so you can see what the size scale is for stars leading up to Betelgeuse. So that in panel 3, the first object is Jupiter, and it's compared to Proxima Centauri, the nearest star to the sun, a red dwarf star in the Alpha Centauri system. And you'll notice that Proxima is not a whole lot bigger than Jupiter, and that's typical for small red dwarf stars. They're super small, super dim, and it's compared to the sun, which, as I've indicated here, is about 109 Earth diameters across and nearly 10 Jupiter diameters. And the sun, I will remind you, heard this from me before, no doubt, is bigger than about 95% of all the stars around. So it's not average, it's not small, it's actually very large. In astronomical terms, it's still considered a dwarf star, but it's bigger than 95% of the stars around, which means the vast majority of stars are basically between the sun and Proxima Centauri in size. Sirius is the next star to it. It's also a dwarf. It's a blue dwarf star, even though it's got to be bigger than 97, 98% of all stars. Astronomy is crazy that way. And so in the fourth panel, the first object is Sirius. And then we see Sirius is a main sequence star like the sun, a fairly big main sequence star. The rest of these, Pollux, Arcturus, and Aldebaran, are red giants. So our sun, in a couple of billion years, 3 billion years maybe, will look like something between Arcturus and Aldebaran in size. It will become a red giant. So Aldebaran, which is a red giant, is the first object in panel 5. And the next object there is Rigel, the blue supergiant in Orion, opposite corner of Orion from Betelgeuse. Blue supergiants are very much smaller than red supergiants, as you can see here, because Antares and Betelgeuse, which finishes out panel 5, are red supergiants and are much bigger, but much cooler than Rigel. The size I've given here for Betelgeuse, about 4.6 AU, is a little less than the diameter of the orbit of Jupiter in our own solar system. It is highly uncertain. We know that it's big, but exactly how big remains to be seen. Betelgeuse is the first object in panel 6, which works its way up to UY Scuti, as I recall. The heads of Zoom cover up part of my slides, and so I can't see the whole slide. I can't remember what the U comes after UI, but it's big. It's the biggest star in linear size that we know now. But it used to be a few years ago, VY Canis Majoris was the biggest, but it's been displaced. And of course, I stole this plot from the internet from people who can't spell Canis correctly. So don't blame me. It's only one end, not two. So already just a quick show what happens with the red supergiant star. Well, the sun fuses hydrogen into helium. It will eventually, when it becomes a red giant star, fuse helium into carbon and oxygen, and then it will stop and it won't fuse anything anymore. And it will cool off, a white dwarf star. And somewhere along the line, it will almost certainly swallow up the Earth and we will be sucked into the sun. So if you're still around in a couple of billion years, it's going to get inhospitable around here. And we need to migrate like to the moons of Jupiter, something where everything will be just great, because about the same time the sun becomes a red giant, Andromeda will collide with the Milky Way, and there'll just be lots of stuff happening all over the place, star forming, galaxies colliding, red giant. It's going to be really exciting around here. But all the nuclear fusion in a red giant is going on way down deep at the core of the star, and a little plug not much bigger than the Earth, 10,000 kilometers, is a little bit bigger than the Earth, very tiny speck at the center of the star, where there's a shell that you're fusing hydrogen, and the ash is helium, and it goes to the helium shell where it fuses into carbon, and the ash goes into the neon, and so on. And so you keep fusing the heavier elements, and eventually when the iron core becomes unstable, the whole thing blows up into a supernova, which will certainly happen with Betelgeuse, but maybe not as soon as you wish it would. This is what's going on inside Betelgeuse, but exactly what's fusing into what inside is not clear. It probably has not reached this stage where you're fusing all the way to iron. In fact, Betelgeuse is probably at the stage where it's fusing helium into carbon and oxygen in its core, just like the sun will be doing when it becomes a red giant. And it's unlikely that the carbon is fusing into anything heavier yet. in Betelgeuse. And that being the case, it's not going to blow up for a million years. So I'm sorry to upset you people, but you may not get to see a Betelgeuse blow up in your face. This is the famous image that Hubble Space Telescope released back in 1996. The only star that you can point a regular telescope at and get an image is Betelgeuse. This is an ultraviolet image, and it's not a real image, which is highly pixelated. So what they did is oversample the image significantly and then smooth it with a bunch of statistical curve fits so that it looks like an image would have looked if Hubble were bigger, perhaps, or had higher resolution detectors. But still, it's ultraviolet, so you're probably sensitive to the photosphere and getting a pretty good depiction of the star here. Whether the star is bigger than the orbit of Jupiter, as is indicated here, or not, depends critically on the distance, and we'll talk about that. So here's some pictures released in 2009 from the European Southern Observatory. Now, the picture on the left is blue plates from the Palomar Digitized Sky Survey, and to the right of it in the middle is the red plates and zoomed in. So if you look at the plate on the left, you see the little rectangle around Betelgeuse in the upper left of Orion. That is the size of the field of view of the next panel. But these two panels, so this is the red plate. If you look in the middle of the middle panel, there's a little blue rectangle way down deep inside that glaring image of Betelgeuse, and that gives you the size of the third panel, which is a high resolution image of the star using the very large telescope and an infrared instrument. And you see now that you're seeing a great deal more than just the star. Betelgeuse, being a red supergiant, has a wind that's about 1 million times stronger than the solar wind that comes out of our own sun. So it's surrounded by shells of gas that cool into dust. It has a complicated circumstellar environment, much more so than the sun. And you can see that environment on this image. So here the image on the left comes from the same crop of observations that you just saw in the previous slide. The bright image of Betelgeuse at the top of the slide is and look like if you could see it up close, emphasizing details that would be pretty hard to see. A star like Betelgeuse has intense convection in the outer layers of the star, so the material is welling up, cooling, and then coming back down. And the speed at which this material flows in the outer atmosphere can be supersonic, and often is, for a red supergiant or even a red giant star. So it goes very fast. And so the star does not have a nice clean surface like you think of when you look at the sun. It has a very bumpy surface. Sometimes the convection currents will make it stick out over here, and it won't stick out so far over here. So if you could actually see the edge of Betelgeuse, it would not be a nice round circle. It would be a bumpy thing, which becomes important when we try to figure out the distance. The whole image is an artist's conception, but the colored material away from that is a really good depiction of what the circumstellar environment looks like. And there's this blue arc out here that I refer to in the text, cool gas arc at about 150 kelvins. This gas is ejected from the star episodically. It's not a steady flow. It's like a coronal mass ejection or flare from the sun, except for a red supergiant like Betelgeuse, that happens all the time. It's just constantly corona mass ejecting stuff. and creating this complicated family of fast-moving clouds outside the star. The image below on the lower right is a radio image made by the E. Merlin Very Long Baseline Interferometry Network, headquartered in England in 2013. This is a 5 centimeter wavelength, which is well into the micrometer, well into the radio wavelengths. The circle overlays, the inner circle is the diameter of the orbit of Jupiter, which is pretty close to the diameter of the photosphere of the star. So that inner circle is probably a good representation for the photosphere, for Betelgeuse itself. And the outer circle is the orbit of Neptune in our own solar system. And as you can see, there's considerable material extending beyond what would be the orbit of Neptune at 30 AU, as there is in the image over on the left, which has a scale bar in AU that also shows the orbits of the planet. So out here, you can see my cursor, is Neptune at 30 AU. And so this is a Neptune distance affair. And likewise out here, we're looking at Neptune distance affairs and quite a bit farther out. So this image, I wanted you to get a good look at the image itself before I throw annotations all over it to show you what you're looking at. This is Betelgeuse in the middle here. Well, the star Betelgeuse is buried in here as a dot. This image is way too big. This image is like 5 light years across. So you won't see the image of the star itself at all. It's a dot buried in the center. But this is that circumstellar environment around it, the gas that's cooling into dust that's been pumped out of this star for who knows, millions of years, forming a nebula around it. It's moving fast, very fast, from right to left. So the wind from the star that's going in the same direction as the star is moving even very faster. And so this long red arc, and there's several, you can see several nested red arcs, are a bow shock or bow shock caused by that fast moving wind from Betelgeuse crashing into the interstellar medium. And if this image is like 5 light years across, this is pretty close to 1 light year in distance between the bow shock and Betelgeuse. And over here is an element in the interstellar medium that's independent of Betelgeuse. But this is really nice, quite smooth. It indicates that the wind is fairly isotropic. So now we'll plaster it with annotations. You can see how it's going. Basically, 67,000 miles an hour or 30 kilometers per second from right to left. And that's very nearly the same speed the Earth has as it goes around the sun, which I think is a little bit slower, like 65 or 66,000 miles an hour. So we're going almost as fast around the sun as Betelgeuse is through the interstellar medium. And the wind is coming off at 17 kilometers per second, or about 38,000 miles an hour. So you combine those two and you're getting something over 100,000 miles an hour is the speed of the wind colliding with the interstellar medium. So basically inside the bow shock, the environment is dominated by the wind from Betelgeuse, just as inside the magnetic environment of the sun, where the planets are, the environment is dominated by the wind from the sun. And when it reaches the limit of the sun's magnetic field, which is very much closer than it is for Betelgeuse, the environment is dominated by the interstellar plasma. So in about 5,000 years, that bow shock will collide with the feature called the straight wall in the interstellar medium, and maybe 12,500 years, Betelgeuse will get there and collide with it too. Not a whole lot will happen because it is the interstellar medium. So even though it looks like it's something, like all the interstellar medium, if you look up close, it's mostly nothing with a little something spread out in it. But it will make for interesting images if astronomers are watching 12,500 years from now. This image is about 5.6 light years across at a distance of 640 light years, as I recall. But probably, maybe, Betelgeuse is a little closer than that, which would make this a rather smaller field of view, maybe only 5 light years, something like that. This is a Herschel image. Herschel is the observatory that preceded the James Webb out at the L2 point. It was a far infrared sub-millimeter observatory, and the different colors are labeled here. Blue is 70 microns, green is 100 microns, and red is 160 microns. This image is dominated by the 160 micron red glow, so you're seeing thermal emission from relatively cool dust. This is the radio image you saw before, was thermal emission as well. So the real issue with Betelgeuse is how far away is it? So back in 2008, Harper and his friends figured that about 640 light years was the distance, doing a lot of parallax data. They upgraded that in 2017 and the distance 724 light years. But as you can see, a lot of uncertainty. So it could be anywhere from 613 to 880. They gave it luminosities and masses that are dependent on the distance. So if that distance is wrong, those numbers are wrong too. The age comes from their model of the star, and they put it at 10 million years old, combining stellar evolution models with their observations of the current state of the star. Again, it depends a bit on the distance. I figure a 20 solar mass star should have a lifetime of about 25 million years before it goes supernova. If these numbers are correct, Betelgeuse won't blow up for 15 million years. Now, I know everybody wants to see it blow up tomorrow. In fact, you're probably hoping that when this meeting's over, you can go outside and realize it blew up during the meeting. But that's not going to happen. Even if these numbers are way off, 15 million years is a really big gap. So in any case, it's probably going to be hundreds of thousands of years before Betelgeuse goes kablooey. And the problem is that the angular diameter of Betelgeuse, which was first measured at Mount Wilson Observatory by Michelson and Pease using the 20-foot interferometer on the 100-inch telescope, and I've chopped out a part of their paper to show here, they got an angular diameter of 47 million milliarc seconds, which is what this is, 0.047 arc seconds. Harper et al. Get an angular diameter 44 milliarc seconds. Everybody agrees with this diameter. It's going to be 44, 45, 46. Different sources give you different, but they're all in the same ballpark. Whereas the parallax is around 4 to 5 milliarc seconds. The parallax that they were using back in 1919 and 1920 is way too big. It's not that big. It's much smaller, which means the parallax angle is about 1/10 of the angular diameter of the star. So what usually happens when you do a parallax measurement is you look at the star, and there it is, and it's a little point, and it bounces back and forth. So it's pretty easy to get that distance because it's just a little thing bouncing. You look at the distance it bounced. But with Betelgeuse, it's a big thing, and it's wiggling back and forth at maybe 1/10 of its diameter. And while it's wiggling, its surface is jiggling because it's a red supergiant, variable, highly variable star. And it does not have a nice round surface. It has a bulgy surface, and the bulges change as convection patterns on the star changes. So it doesn't always have the same shape. The shape isn't round. The shape is constantly changing. So all of these things induce errors in trying to figure out how much of the motion you're seeing is the edge of the star change and how much of it is the star itself systematically moving back and forth by 1/10 the diameter of the star. So there are big uncertainties, and always will be, in parallax and therefore the distance for Betelgeuse, because it's super hard and in some sense almost impossible to cleanly separate the squiggly motion of the edge of the star from its tiny parallax displacement. So the most recent analysis on this I can find comes from October 2020. And here, the scientists, aside from looking at all the data that everybody else looked at, whatever parallax data they can get from radio sources, things that might not as much on the angular diameter, and they have calibrated this by looking at the helioseismology. That's what I call it. Asteroseismology is the correct word. Helioseismology applied to other stars. They're looking at the vibrations of the star, and they can see periodic vibrations and tell whether they're looking at an overtone pulsation, regular tone. And from that, they can diagnose the interior structure of the star and what its real radius is, its physical size. And from its physical size compared to its angular size, they can get a distance too. So they compare or combine all these data, and they come up with a very much closer distance, only 168 parsecs or 548 light years. So far we've seen 640, 740, and now 548 as people try to figure out how far away it is. Now they say from their models, applying asteroseismology to Betelgeuse, they say our results place Alpha Orionis definitively in the early core helium phase of the asymptotic giant branch. If it's in the early core helium burning phase, that's what I was talking about before. It's not fusing the heavier elements yet, and it's not going to go supernova until it fuses everything all the way to iron. So it's going to be a minimum hundreds of thousands of years before it blows up, and most likely several million years, because if it's early in the core helium burning phase, it's going to burn for a while like that before it starts fusing the heavier elements. As the heavier elements begin to fuse, the schedule goes faster and faster and faster. And so the last few stages where you fuse everything into iron go in a few days. And so when Betelgeuse really does blow up, it's not going to do anything dramatic where you can see it in advance. It's not going to change its brightness, change its size. Not going to do. It's going to be in your face. It's just going to blow up suddenly because there's no time for the outer layers of the star to react to the very fast process going on inside. So even if you do see Betelgeuse do something fascinating, don't bet on a supernova, because it's not going to happen like that. They also give a somewhat lower mass, perhaps as low as 18 solar masses initially and maybe 16 now. But they also show us a plot of the recent published values for the distance using Hipparcos parallaxes, VLA radio, revised Hipparcos, other radio data, and of course there's seismic calibrated data in this paper. And if you go to the top of the error bar for the highest distance, and then the bottom of the error bar for the lowest distance, the distance range is from 360 to 880 light years. And really all you can say with any kind of confidence is that Betelgeuse is somewhere between those two. And that's a big discrepancy in distance. And so you can't really say you know how big it is, can't really say you know what its mass is, how bright it is, because the distance is way too uncertain. So it's probably more than 10 solar masses, but who knows? It could be 15, 25. It could be 50,000 times brighter than the sun, or 150,000 times brighter than the sun. You just don't know. It could be as big as the orbit of Jupiter. It's not as small as the orbit of Mars, like they thought in 1919, because we know the parallax angle is surely smaller than that. But it's somewhere between the orbit of Jupiter and the orbit of Mars for the diameter of Betelgeuse. So it's big, maybe not as big as we wish it were, but since we don't know the distance, we just don't know how big it is. And it's going to be that way for a long time. We're just not going to nail down the distance to Betelgeuse, really. So this plot has nothing to do with Betelgeuse. This plot is circumstellar shells around another Mira variable red giant star. But back in 2009, about the same time those VLA ESO images were coming out, Charles Towns, the late Nobel laureate, who ran ISI infrared spatial interferometer at Mount Wilson Observatory, pictured here, they were observing Betelgeuse at 11.5 microns in the far infrared. And they reported that over 15 years, its size decreased by 15%. And if you can remember back in 2009, people saw this, everybody went outside and was waiting for Betelgeuse to blow up, because everybody wants it to blow up. But as I said, if you see something like this is almost certainly not an indication that the star is going to blow up, because the things that happen to make it blow up happen too fast inside the star. And it's simply not going to give you 15 years of warning. It maybe give you 15 minutes of warning, but not 15 years. Just not going to happen. But if it did blow up, we all want to see it, how bright would it be? Well, the plot on the right is a line plot showing you the most likely brightness in the optical and total, which is bolometric. That means radio, infrared, everything. How bright would it look in time after explosion? The plot on the left is a broad band, because there's lots of different ways to model how a star like Betelgeuse could blow up. It depends on the distance, and they know very well how uncertain the distance is. And as you can see from the text I put down on the lower right, they were assuming the 640 light year distance from Harper et al. 2008. But there's lots of other values. And so that envelope gives you uncertainty in the distance, possible models for the explosion. So, but even if it's at its dimmest, if Betelgeuse did blow up, it would be brighter than Venus and almost as bright as a full moon. But you know, you can see how bright Venus is at night, and you know you can see it during the day if you know where to look and how to look. Venus is a daytime naked eye object, but it will be a couple of magnitudes at least brighter than Venus, and maybe more than that, maybe 5 or 6 magnitudes brighter, in which case you'd see it in the daytime without any problem. And that would last for a long time afterwards. And the authors remind us that Betelgeuse could leave behind a neutron star. It may or may not make a black hole. It's pretty massive, probably. And so most likely, I think it would leave a black hole behind, but maybe not. It could leave a neutron star. And that's what's powering the Crab Nebula. It glows because of a pulsar in the middle of the nebula. And so if you put the Crab Nebula at the distance of Betelgeuse, then it would be about 1 degree across in the sky, and it would have a visible magnitude of 3.4. It's an integrated magnitude, I think, over the surface. So its surface brightness would be less than that, but in the dark sky, it would be a very conspicuous naked eye object in any case. So if Betelgeuse created a supernova remnant, and a remnant with the neutron star, a pulsar in the middle of it, it could glow for just years and years as a naked eye object in the sky afterwards, powered by that rotating neutron star. And so now you know what the explosion you're not going to see, sorry about that, would look like if you could see it. So we'll have to hope for some other star to go supernova sometime soon. So we talked about how bright it could be. How about dim? You recall, as the pandemic set in, so did the great dimming of Betelgeuse, which suddenly went into the tank down to about magnitude, almost magnitude 2, about 1.7, 1.75. Historically, around 1.5 is its dimmest magnitude. So the great dimming of 2020 was significantly dimmer than you would normally expect. Not literally unprecedented, but very strange. And you can see this light curve that comes from the AAVSO, the American Association of Variable Star Observers, who used to own Clinton B. Observatory before we got our hands on it. You can see that it generally has been hanging around, 0.7, 0.25. In 2019, at the beginning of 2019, it dimmed down to first magnitude, a little dimmer than it normally has for the last several years. And then, of course, it went into the tank and rapidly recovered in 2020. So once again, there's lots of hopes for a supernova explosion, but that's not going to happen. Probably what happened was a cool patch exposed on the surface of the star. Remember, the convection, the hot stuff comes up, spreads out, forming a cool patch. As it cools, it makes a cool patch and then goes down. Well, in this turbulent convection, you can get a persistent cool spot on the surface of a star like Betelgeuse, where there's a persistent hot spot somewhere else. And this persistent cool spot means it's not radiating outward the way it used to. And so the stuff out there, the circumstellar shell, circumstellar gas, will cool into dust, and it will be dark too, and that will block part of the view. So these 4 vertical blue lines you see on the plot correspond to these 4 images: January 2019, December 2019, January and March 2020. So in January of 2019, where Betelgeuse had dimmed to almost first magnitude, you see the star has its usual shape. But in 2019, the southern hemisphere kind of goes dark. And by January 2020, the whole thing has gone dark. And then by March, it's brightening up again and it's coming back. So what probably happens here is that, as I described, you get a cool patch, and that cool cloud of dust is coming towards us. Maybe it's spreading out and just sort of blocks the whole star, but not for long. It dissipates, it spreads out, the star can shine again. The cool patch on the surface goes away and is replaced by a hot patch. And that seems to me the most reasonable explanation for what caused the dimming. People are still arguing about it, arguing that some other big cloud moved between us and Betelgeuse, which I suppose is possible, or some strangeness going on with the nuclear reactions in the core, which I don't believe. That doesn't make any sense. So I think the changing of the surface is the way to go. Now, there is one other problem I want to discuss, and that is that we know Betelgeuse is a red star. And Ptolemy, back in 100s AD, recorded as a red star, and it's been red to everybody ever since. However, 200 years before Ptolemy, in the 100 BC region, Chinese astronomers recorded Betelgeuse as being yellow, not red. We don't have any other ancient observations to compare with, so we're left with a quandary. Were the Chinese unable to tell the difference between red and yellow? Highly unlikely. Is it some kind of a mistake? Did somebody write something down wrong? Are we translating the ancient Chinese wrong? Possibly, but ancient Chinese is a pretty well-known language. The linguists are all over that. It's pretty unlikely that we're going to screw up and get yellow where it ought to be red. It's possible, but it seems unlikely. So what is the source of yellow Betelgeuse in the ancient Chinese records? Well, it could be any number of mistakes, who knows? However, there is a stellar evolution pathway that could explain it. So the diagram you see on the right is an evolutionary path on a Hertzsprung-Russell diagram, like the one I showed before, and you see again here on the left. Now, this is the evolution diagram for a 5 solar mass star, which is the only one anyone shows me for yellow supergiants. So the top part of this plot is not a good indication of what will happen to Betelgeuse. Forget about post-AGB and white dwarf. Betelgeuse is going to blow up. It's just not going to blow up soon. But the part that's labeled blue loop in the center is probably a good description of what can happen to a star like Betelgeuse. So the sun is a main sequence star. Betelgeuse used to be a main sequence star, blue over in the lower left corner. Then it becomes a subgiant, and then a red giant. But for stars with the right chemistry, with the right mass range, they go through an evolution pathway different from the sun. So our sun will become what's called a horizontal branch star, but a more massive star will not do that. A more massive star will go through what's diagrammed here called the blue loop evolution, where it suddenly heats up, gets a lot brighter, and moves back towards the blue end of the Hertzsprung-Russell diagram from the red end where it is, and then eventually moves back to the red and then becomes a red supergiant star. This blue loop evolution happens very fast by astronomical terms. A star will be a yellow supergiant only for a few million years at most, and maybe less than that. And depending on the mass, maybe only a few thousand years. So there is this thing here called an instability strip. And as the star evolves now, when I'm talking about the evolution of the star, I'm talking about its observational properties. We can see its color, we can see its brightness, we can see its temperature. I'm not talking about what happens inside the star in the nuclear fusion regime, because that's kind of unclear what's actually happening. But we do know how they go through their observational evolution. And the star inside this area called the instability strip is called a yellow supergiant, and also a Cepheid class, excuse me, a Cepheid class variable star. And if you look over here on the left at the HR diagram, there's the giant branch with Aldebaran, Pollux, and Arcturus in it, we looked at before when we saw the sizes of the stars. Betelgeuse and Antares are red supergiants up here. And in between them over here is Polaris, a star you should have heard of, which is a yellow supergiant and a Cepheid class variable star. And so it's possible that a few thousand years ago, Betelgeuse was right at the end of its blue loop evolution, and we don't know what color it had before that because we don't have any good ancient records that I'm aware of what Betelgeuse looked like way before the Chinese said it was yellow. It's possible, just possible, that Betelgeuse was actually yellow. And this is a third point. If Betelgeuse actually just climbed out of the blue loop and was a yellow supergiant a few thousand years ago, is now in the red supergiant branch, that again is an indication that it's not going to blow up for millions of years because it has to go through the red supergiant branch evolution first. So this actually agrees with the Joyce et al. Conclusion that it's at the base of the helium burning phase of the red supergiant branch. So I know I've dumped lots of water on the hopes and prayers of people to see Betelgeuse blow up. I'm afraid that's just not going to happen. You're not going to see it. But I will point out that this is not the only problem like this in astronomy. Some of you may be familiar with the red Sirius problem because there are ancient records which describe Sirius as a red star. We know that Sirius is a blue dwarf, actually. It's a blue main sequence star, and there is no stellar evolution pathway that will make Sirius red. You just can't do it. Sirius was never red. So why did it look red to somebody? Was that a mistake? Was that a mistranslation of some ancient word? I don't know. Nobody knows. People have suggested that some wandering interstellar dust cloud coming between us and Sirius would make it look red, just like smoke makes things look red when we see through them, or red sunsets and all that. So that's possible. Who knows? The red Sirius mystery is still a mystery, and nobody knows the answer. And actually, the yellow Betelgeuse mystery is still kind of a mystery, but it's one that could be explained maybe by stellar evolution, which you can't do with the red Sirius problem. And with that, I hope I've told you enough about Betelgeuse to make you happy. And I will bring my formal presentation to a close and take questions or whatever else you want to do.
Super job.
Take it away.
Thank you.
Thanks.
Questions?
Good talk, Tim.
Thanks.
So there's a lot of question that came up in the chat about, have we gotten better, or do you think we've gotten more precise at understanding when a particular star or particular class of stars is going to go supernova, and within our I guess all humans want to know within our lifetimes? My answer was, I don't think so, because astronomy is just way longer than our lifetimes, but I thought I'd pose that question.
Have we gotten better and more precise than we used to be? We certainly have. Have we gotten good enough and precise enough to tell everybody to watch out because next year at this vernal equinox, our favorite star will blow up? No, we can't do that. We know the conditions that lead to a supernova explosion, and we can derive an age with some uncertainty from stellar evolution models. So we can pick out a star and say that star is a candidate for supernova, but invariably it's going to be that star could blow up tomorrow, or that star could blow up in, say, 1 million years or 500,000 years. And you're probably not going to get much better than that.
Thank you.
Because you saw the image I showed earlier of what's happening inside a supergiant star, and that'll make you all dizzy by, oh heavens. So there, let's do that. So this, the nuclear physics that goes on inside this core goes faster and faster as you go down from hydrogen fusing to helium fusing. So what happens is that the star starts out as a red giant, it's fusing helium into carbon and oxygen, and that takes a long time. Then the carbon and oxygen fuse into neon. Okay, that takes less time. And the neon and the oxygen, they fuse into silicon and a bunch of other stuff. That takes less time. And the silicon fuses into iron goes very fast. So that the trigger for a supernova explosion happens too fast for you to be able to look at the outer layers of the star and see a clue that tells you deep inside it's going to blow up. Now, the only exception I can think of to that would be asteroseismology, which the Joyce people did, because the vibrations at the outer layer of a star will tell you what's going on inside the star. But I don't know, and I don't think anybody else knows either, how much precision you'd need for those observations to be able to make such a close, fast observation of a supernova explosion.
So I guess we're fortunate there are thousands and thousands of galaxies to watch for for a supernova.
Sure, there are supernovae going off in other galaxies all the time. People are constantly discover them. There are supernova hunters that go out and check their galaxies every night for supernova. It's, of course, what you want is one close enough to be interesting,
Not too close.
too close. You really don't want to be too close to a supernova. That's not a good place to be.
Is it true, though, that we're not really sure of any massive supergiants in our area that would cause us problems?
That's true. There are no stars close enough to us to cause any real problems if they blew up. And the only star close to us, really close, I think, maybe, that we know is a candidate is Betelgeuse. But from all appearances, it's not going to go off anytime soon. And there's no other star as close as Betelgeuse that you could look at and say, that's probably going to blow up someday. Supernova in our own galaxy are basically invisible unless they're really close, because the dust, we're in the galaxy. So we're in the plane of the spiral arms and the dust, and that dust blocks out any supernova that we might see.
Will the JWST help with that?
No, I don't believe they will. They're not well equipped for that kind of thing. What you really need is a radio search to find those. And that's one of the early projects I worked on at JPL. That was a really nice and interesting project, so it didn't get funded. But we were going to scan the Milky Way with the
Laugh out loud.
Yeah. We were going to scan the Milky Way with the radio, with the big antenna at the Goldstone, like once a week.
Tim.
And you're welcome. And look for transients, but you need radio to do that.
Tim, when you're changing from one fusion to another, is there no outward appearance change in Betelgeuse? Like by the time it's changing carbon or neon, does it look different?
No, it looks pretty much the same. It bloats out into a red supergiant, and it's so dynamic that you can't tell. The thermodynamics of the atmosphere is going to override anything you're getting from the core, which is very small.
Okay.
So you're not really getting any clues. So you have to guess what stage you're in from the age that you get from your stellar evolution model. So there's always a lot of uncertainty. What you really like to do, of course, is fly into the star, go down to the core in your magic spaceship and look at it and say, oh, hey, that's only fusing neon. We've still got, but that's kind of hard to do. It's like why I tell people you can't send a probe into the sun. It doesn't work.
Okay. Any other questions? Was there any other in the chat?
I think
So
there's 70
what's the approximate time span from hydrogen fusing all the way to supernova?
Hydrogen fusion all the way to supernova depends very much on the mass of the star. High mass stars like Betelgeuse no more than a few tens of millions of years. Like I think the lifetime for a 20 solar mass star is about 25 million years. And if you make them bigger, that lifetime cuts off pretty quick. And of course, for the sun, it's like 10 billion years. And so it's dependent very much on the mass.
Okay, but so what about from carbon to supernova? I mean, yeah, helium and hydrogen is probably very slow process, but
yeah, it always depends on the mass, but you require a really massive star to fuse carbon. Like the sun will fuse helium into carbon and oxygen, but it will not fuse carbon and oxygen into anything heavier. It will be a carbon oxygen white dwarf.
Right.
Helium. It won't do anything bigger. The bigger star, it will be from a few tens of millions of years down to really fast. And some stars are never stable, and they may last only like a million years, do all their fusing, and then just blow up, like the big supermassive, the Eta Carina and the 100 solar mass stars. Those are things that could blow up any minute, literally.
There are a few questions. Yeah, there are a few questions in the chat about, I guess, if what would be worse than being near the bow shock waves when you as Betelgeuse is moving fast.
I mean, if we were there.
Yeah, I think that's what the intent of the question.
Yeah, that material is. So the wind coming out from Betelgeuse like a million times the wind coming out from the sun, but a million times the wind coming out from the sun is not much by our terrestrial standards. And when you're that far away, that the bow shock is a light year away from Betelgeuse, it's to you sitting there, it's going to be interesting if you have instruments that can sample the plasma, but your big worry won't be the bow shock. It'll be hanging around in the vacuum of space, which you need to be careful about. That will be your problem, not the bow shock.
Tim, there's another question that's interesting, and that was, if we have probes that are very far away from Earth right now, further than say Hipparcos or whatever, would they be able to get a better handle, or probably not equipped to, but maybe, on the actual size of Betelgeuse, or is it more a matter of the star refuses to cooperate?
They wouldn't get a better handle on the size, but they certainly would get a better handle on the parallax angle. And that,
well, I think that's what people are thinking. Yes.
Yeah. And that, in fact, was a mission proposed by Aidan Meinel at the University of Arizona, Tucson. He and his wife were on the faculty there. Optics was his big thing. Back in the 80s, I think it was, called the 1,000 Astronomical Unit mission. And they proposed to send a telescope out 1,000 astronomical units, which would take about 50 years to get there. And then do parallax instead of using the 2 astronomical unit diameter of Earth's orbit, using the 1,000 astronomical unit diameter between us and that and the Tau satellite, to do parallax measurements, and you could see practically all the way across the galaxy. Betelgeuse is a big star. You'd probably still have problems, but you'd certainly be able to do a much better job getting parallax with a mission like that. But it didn't get funded either because it takes 50 years for it to get there, and nobody in Congress wants to fund something that will happen after they can claim credit for it.
But even for 1,000 AU satellite, it would take hundreds of years to go from one end to another end, right? To do the parallax.
Well, for a satellite to get out there, you could do it in about 50 years. But for 1,000 AU, of course, the light travel time wouldn't be that bad for the signals. But it'd take about 50 years to get there.
Thank you.
Yeah.
Okay, well, Spencer, why don't you post the prize
Yeah, I just
link one more time? And
okay.
I'm pretty sure I was able to post the Mount Wilson dates and information, how to get a hold of me in the chat as well.
Yes, it came through the chat.
Okay, great. So everyone can look back through and you see the dates that we have for Mount Wilson. Right now, all of those dates have openings. So there's not a huge rush. I didn't get 50 people that wanted to sign up as soon as I opened up the dates. So it's going to go kind of like it usually does. We'll start filling them up pretty regularly. A few people have dates that they want in the later of those dates, and that's fine. So just let me know. And some people want later in the year because they want to see different things. So.
Oh, hello. Yeah, this is Jack here. I'm still trying to ask that question of Tim about how long is the length of time the iron fusion. In other words, hydrogen to helium is millions of years, and by the time it gets down to iron, cobalt, whatnot, what is that around? Minutes, days, months?
It's a few days. Yeah.
A few days. Okay. Mm-hmm.
Yeah. It's fast.
Yeah. Oh, okay. Sounds good.
All right, I've just reposted the link for the drawing. There are about 30 people who signed up. I think they're close to 60 on the call.
Oh, but there's only 46 left, right? So everybody leaves so I can win a prize.
Dude, you've won so many prizes.
What Tim needs is another hat. That's what Tim needs.
Oh, yeah.
No, I think after your Christmas one, I think you're done.
Okay, I'm going to close out the drawing now in about another 30 seconds.
Thank you, Tim. And thank you for jumping in tonight to do a talk. We were not quite prepared for this evening with an outside speaker, so Tim jumped in and, as always, gives us more information than we can almost possibly digest in one sitting.
Absolutely.
Thank you, Tim.
Thank you,
It was
Tim.
interesting.
Wonderful.
I promised to use it at summer camp because I can point at the star and tell them more about it now.
Oh no, you have to use the figures too.
Yeah.
Don't worry, I'll get every number correct in the middle of the night.
Also, everyone remember that these are recorded and you can go see them on our YouTube channel. So if you missed something or you want to see some of those charts again, you can always go and rerun.
You mean all my stupid comments have been recorded?
Absolutely.
Oh my God.
Watch your language, everybody.
That's why we put everyone on mute, because we don't hear what you're saying while Tim's talking.
Okay, so I'm ready to start the drawing if you guys are.
Alicia?
I'd be ready.
Yeah, I'm ready.
Okay, here we go. Let me share this. All right, drop the first set of names in there. Okay, Annie is the first one.
Yay. So Annie won a Amazon gift card for $25.
Thank you.
Okay, next one is Jeff.
Jeff,
Jeff, there you go.
Yeah, see, all that helpful commentary paid off.
Yeah.
That is so awesome. What did I get? A signed card by Tim Thompson?
You can get that any Wednesday at Garvey.
That's right.
Oh, I see.
He only charges $25. It's a good deal.
Alicia hasn't told us what you won yet.
Now, what did Jeff win?
Good. You laughed. Sorry. Jeff won a LAAS hat.
All right.
Oh, yes. Way
Okay.
to go. Thank you.
Okay.
Next one, Jeremiah.
Cool.
Jared,
There
Maya,
he is. There he is.
a laser.
You got the
Oh,
laser,
nice.
dude.
Cool. Lucky.
All right. He looks happy.
Okay, next. Mark Salzman.
There's Mark. I see him, I think.
That's cool. What did I win?
Mark won a Celestron Observer's map of the moon.
Okay. I don't know what that is, but I like it.
So if you get lost on the moon and stop at a Texaco,
What?
Okay.
What? No. So John was
The
looking-
man with the star. Remember the ad? The man with the star.
Wow.
I was thinking the old road maps they used to hand out, but I'm dating
No, it's
myself.
really cool. It's this really cool foldable pamphlet that shows maps of the moon.
You can trust your car to the man with the star.
Okay, next is James Rufford.
Hey, Jim. Is Jim here?
James won a red flashlight.
Okay.
Guess I dated myself, huh?
Sure did.
Ernesto.
Won an item from the LAAS store.
Oh,
And
that's a good one.
Would I win?
you won an item from the LAAS store.
All right.
We got all
Go to
kinds
the
of cool stuff
LAAS
out there.
website to the merchandise
Does
tab.
it get mailed to my house or?
It's a
Yeah.
signed presentation from Tim.
That's right.
You really
You,
won.
you have to tell Alicia which item you want.
Oh, okay.
Yeah. I send out emails for that.
Oh, thank you.
Also,
Yeah.
I'll follow up with Greg later. Okay. All right, and that was the last one.
Oh, that was the last one. Okay.
Dan, you missed
Oh,
out.
Dan.
Hey, Dan.
Bye-bye.
So Alicia, do you send me an email or do I need to send you one or how does that work?
Who am I talking to?
Jeff.
Jeff. Oh, okay. I'm sorry. I see a little square corner on my iPad. So I send out emails to the winners and you respond with the information and I go buy it for you to your address. And I send it to your address.
That's
Delivery.
So
With
for
the
you
cat.
in particular though, Jeff, because you want an LAAS hat, I have to forward your contact information over to Joe Phipps and Joe will send you the LAAS hat.
Awesome.
Yep.
Thank you so much. Thanks for all your work.
No problem.
Okay.
I like your background.
So that's the end of the contest?
Yep.
Okay. Well, that's all of the business we have. We're certainly, everyone can unmic and chat and have any other questions for myself or Tim, or we can
Thank you.
we can
Tim.
officially
Usual.